Hello and welcome to the second part of Unit 2. In Part 2 here, we're going to learn about velocity and speed. Let's start with speed. Speed is a distance traveled in a time interval. In physics, we calculate a speed by taking distance divided by time. To give you an example of this, if you travel, say, a distance of 40 meters in 5 seconds, then your speed would be 40 meters divided by 5 seconds, which is 8 meters per second. One important thing to notice about speed is that it is based upon distance. As we learned in part 1, distance is a scalar, and since distance is a scalar, speed is a scalar. In your car, you have two ways of determining your speed. One way is you can use your speedometer. This tells you how fast you're going right now. The other way is you can use your odometer. Remember, the odometer is the dial that tells you how far you've traveled. And a clock. This is going to tell you how fast you went over the trip. These two measurements are both measurements of your speed, but they're not the same. The first one is your instantaneous speed. Your speed at any given instant. You might be moving 30 miles per hour, you might not be moving at all. The second way of calculating your speed is an average speed. And it's going to kind of smooth out everything that happened. The example we did on the last slide, where I told you you went 40 meters in, what was it, 5 seconds, 8 seconds, something like that. That was an example of an average speed because nowhere in there did we discuss what that 40 meters looked like. How was it traveled? Did you do it all at once? Did you start from rest? Did you end at a stop? What happened in there? All we know is you went a certain distance in a certain amount of time. Which brings us to the next question. Your average speed on a trip, starting and stopping at rest, is 50 kilometers per hour. Is your instantaneous speed ever more than 50 kilometers per hour? Well, if we think about this trip, here we are at your starting position. I tell you, you start and stop at rest. Here you are at your ending position, also at rest. And over the entire thing, 50 kilometers per hour. In order to start and stop at 0 kilometers per hour and have an average of 50 kilometers per hour, somewhere in the middle, you have to be going greater than 50 kilometers per hour. Otherwise, it would not average out to equal 50 kilometers per hour. Velocity, unlike speed, is a vector. It is based upon displacement. There are two ways of calculating your velocity. If I want to know the instantaneous velocity, that would be v, and I would calculate it using a derivative. And I want not an x there, I want an r, so it could be in any direction, so dr dt. On the other hand, if I want the average velocity, also a vector. Oop, and I'm trying to write an x again. Here we go. That would be a change in position over time. Okay. So two ways of calculating your velocity. One by taking a derivative, the other by just looking at where you start and where you stop over the entire trip. Okay. One thing to remember is that derivatives are slopes. So if I am given a graph of position as a function of time, I can find the instantaneous velocity by finding the slope at any point on that graph. So let's contrast the ideas of velocity and speed. Is it possible to have a non-zero average speed and a zero average velocity? So for an average speed, speed is distance over time. Oops. If this is going to be non-zero, I guess, so it's got to be something that's greater than 0 because it's a scalar. In order for this to happen, for our speed to be non-zero, that means that we have to have gone somewhere. We have to have moved some distance. For velocity, average velocity, that is a change in position over time. So now the question we have to ask is it possible for us to have gone some distance but not have a displacement? And the answer there is yes. Okay. So a good example of this is, again, doing one round trip. I have traveled a distance. I went around the entire oval. But since I'm starting and stopping at the same spot, my average velocity, my change in position divided by time, equals 0, and therefore the first question has an answer of yes. The second question reverses it. Can you have a non-zero average velocity and a 0 average speed? For my average velocity to be non-zero, I have to have some displacement. And if, again, I've had some displacement, then I have to have traveled some distance to get from an initial position to a final position. And therefore, my speed cannot be 0. So the answer to the second one is no. Can your average velocity ever equal your instantaneous velocity? Or in other words, can V equal delta x, I keep doing x, delta r over delta t equal dr dt? And the answer there is yes. Average will equal instantaneous when position is constant. Can't spell, constant. Or when velocity is constant. If our velocity is constant over a given time period, then the slope for the entire time period will equal the slope for the instantaneous at every instant. So yes, your average can equal your instantaneous. One important piece to remember is that for your instantaneous velocity, the magnitude of it, the size of it, how fast it says you're going, the magnitude of your instantaneous velocity is your instantaneous speed. The same is not true for average, unless you have the situation where your average equals your instantaneous. In the last part, I want to think about, well, which one of these cars could actually have a constant velocity? Remember, velocity is a vector. It has both a magnitude or size, and a direction associated with it. So which one of these has a constant velocity, meaning it has both a constant magnitude and a constant direction? We can see that car 1 is decreasing speed, so that means its magnitude is decreasing. So number 1 is out. A car traveling in a straight line with constant speed. Because it's going in a straight line, that means that its direction is constant. And we're told that the speed is constant. So number 2 is an example of constant velocity. We see number 3 is traveling at a constant speed. However, it is traveling in a circle. Because it is traveling in a circle, that means the direction is constantly changing. Because the direction is changing, the velocity is not constant. And the last car has a non-constant direction and a non-constant magnitude. Therefore, it is not a constant velocity. So out of the 4 cars we have here, only one has a constant velocity, and that is the one traveling in a straight line at a constant speed. This concludes part 2.